Hi there. Today we're looking at Longformer, the long document transformer by Isbeltaji, Matthew Peters, and Armin Cohen of Alan AI. So the Longformer is a variant of the transformer, as you might have guessed. The Longformer is a transformer that can deal with long documents. So it's aptly named. So I am going to discuss what differentiates the Longformer from the transformer. If you don't know what a transformer is, watch the video on attention is all you need. I have a video on that. And I would also suggest you watch the video on BERT, because a lot of the architecture and training here is based on the BERT or variants of BERT. So I'll basically explain what makes the Longformer different such that it gets long documents, right? Such it can be applied to long documents. All right, so what is the problem with the original transformer? If you have a transformer model and let's say you're doing an NLP task, which usually is where transformers are used, and you want to have a paragraph like this one right here, the abstract of the paper, and maybe you want to predict whether the paper gets accepted at a conference or not. Now, the classic transformers, they have a limit, a very harsh limit on the amount of tokens that they can look at the same time. So what you would do in a classic transformer is you couldn't process this entire thing, let's say. You would divide it in chunks. You'd say, okay, here's my first chunk from here to here. My second chunk from here to here, and then here to here, and so on. So you go through the document, split it up in chunks, process each of the chunks individually, and then maybe aggregate the predictions. But of course, the drawback is that the model cannot make specific connections between, let's say, some word here like operation and somewhere down here like language. It cannot connect the two on a neural level, at least not in the classic transformer architectures. Now, there are ways to try to alleviate this, but classically, if you split up your documents into individual samples, they become independent. You cannot do attention. This attention mechanism cannot operate across the boundaries of these chunks. So the Longformer, the goal is to actually just be able to put this entire document here into the model at the same time. So let's look a bit closer into this. In a classic transformer model, what you'll have is you'll have layers of what is called attention mechanism. I'm going to draw 6 units here, and the units are actually the input sequence. So in a transformer, other than like a classic neural network, you don't actually have numbers of units in the layers, but you can input as long sequences as you want until your memory limit is reached, basically. So these units, they expose something called keys on the lower layer, and these are vectors that point somewhere, and the upper layer will produce what are called queries. And again, I invite you to look at the Attention is All You Need video if you want more explanation. And basically, the keys and queries, they decide where information gets routed to, right? So the routing of information is what makes the transformer. So for example, this here is probably going to be routed to this here. So the information is routed like this. And then this here is going to be routed like this. You see, the routing is according to the dot product of the keys and queries, right? So in essence, if you have n input sequence tokens, and you usually transform in a transformer, you transform the things into same length sequences. That has to do a lot also with how you want to pre-train things and so on. So we're not really gonna change that part. If you have n input sequence and n tokens on the next layer, and everything can attend to everything. So all the inner products are computed, right? Everything is connected to everything. That means that you're going to end up with an O of n squared memory requirement because you have n squared connections. The way to alleviate this is much like you would alleviate this in a classic neural network. So in a classic neural network, imagine you have this MLP, a multi-layer perceptron, or what usually known as a fully connected layer, right? So here I have the same thing, but it's not a transformer. It's a classic neural network, fully connected. So I have D units right here, and D units in this first hidden layer. And I'll have a weight matrix in here, right? And the weight matrix means everything is connected to everything, right? Everything connects to everything else. Again, my memory requirement here is D squared. Now, how do we deal with this in a classic neural network? We go to what is called a convolutional neural network. At least that's one of the methods. So let's make this again, but let's now make this a convolutional neural network. What we'll have is we'll have a convolutional kernel. In this case, it's just of length 3, right? So we just have 3 units here, and they will do the same fully connected pattern, but only over these 3 units right here. And then we slide the kernel over, right? Now it's in this position. It's still the same 3 units, but now these 3 things are connected to these 3 things that they're now over, right? And so you keep sliding this over across the lower layer until you're finally at the end here. And now you've reduced the memory consumption from D squared to just D times, and if this is usually the kernel size is called K, to D times K. And K you can keep pretty much constant, so that's O of D, right? The same goes for the Longformer. So in the Longformer, the idea is that you have a so-called sliding window attention. It's exactly the same as it is in the convolution, except that you don't have these hidden units here, but these are actually the parts of the input sequence, and instead of the weight matrix here, you have the attention mechanism over the keys, queries, and values. But the idea is similar. So you can basically say this is a sort of a convolution, and we've already had this in the video about axial attention a bit. Now, of course, this is you trade off memory for performance, because before, right, I'm gonna let's draw it on top of this fully connected layer. Before, all the units could attend to all the units, right? And now the unit can only attend to its immediate neighborhood, right? This green unit here can only attend to itself in the lower layer and its immediate neighbors if the kernel size is 3. But consider what happens in the next layer. So in the next layer, I have, for example, this unit right here. This is same unit, right, on the next layer. It can attend to these 2 and itself in the lower layer, but these 2 themselves can attend to all of these, right? So that the one on the right can attend to one more. So in the first layer, this particular unit had information from these 3 units, but in the second layer, the same unit has now information across these 5, right? And this is kind of this cone of attention. It gets bigger and bigger as you go through the layers. So you lose the information to incorporate wide ranges of information in a single layer, but you regain it through depth, right? The deeper you go, the more a single unit gets information, right? This unit gets information from this unit over here through the layers, It can't watch the unit right here in this layer. That's not possible, but it gets the information through the layers. Of course, there's still a trade-off, like a fully connected layer could just do this in one step, and then in the next layer, it could do it again, right? It can do much more complex computation. But if you believe that the most important information is actually in the neighborhoods of the individual tokens, which is conceivable, in something like a convolutional neural network, you know that, in an image, usually you have localized information, right? If there's a cat here, then the nose and the eyes of the cat are pretty close together. So in order to recognize it's a cat, you mostly want local information, more and more local information. So in an image that makes sense, and in a text it also makes sense to a degree, in that usually words close together in a sentence, they are important for each other, right? But the power of the transformer was initially that it could attend to everything in a sentence, right? So for example, if you have again the paragraph here, the power of the transformer, at least that was said, is the fact that this piece of text here could make a connection to this piece of text here, and therefore the understanding of the entire paragraph could be reliant on this connection being made, which a local model can't do. But if you go through depth, that you might be able to recover that. So the Longformer is basically what the convolutional neural network does for MLPs. It does it for transformers, right? So instead of n by n giving you n squared, now you go into this way where you have, so if you do the same for the transformer, you go to O n times, let's call it W, and W being your window size in this case. They have an illustration of this right here. So in a original transformer, this is an attention matrix. So here you have your n units in a sequence, and drawn in is which unit can attend to which other unit in a given layer. So you'll see this particular unit I here can attend, of course, to itself, right? Can attend to unit I, but it can also attend to this unit, or to this unit, or to this unit, to any unit, right? And that's what gives you this n squared attention, because any unit can attend to any unit. Now, in this sliding window attention pattern, and this is one of the core components of the Longformer, you see that the ith unit here, right here, can attend to itself, right? But also to this, and to this, but no more. It can only attend to the ith unit, or to I minus W to I plus W, right? And this here is a window of size W. This is this sliding window. So a given unit can only attend to itself or its neighbors in one layer, right? And this is exactly what a convolution is. Like if you see this pattern, this is a convolutional pattern. Now the second core component is they expand on this idea in that they create these dilated sliding windows. Now you already know what a sliding window is. Now they're saying, well, if you have this sliding window, it might take quite a number of layers in order to, get your attention of the entire sequence incorporated. We saw before it took like 3 layers to get halfway through this sequence of, what was it, like 6 tokens, and it took us like 3 layers. And so basically, if you go 1 layer up, right, 1 layer up, you gain 1 more context window in each direction, right? So it's not you'd have to go very, very deep in order to incorporate the information from these very long sequences. And the dilated sliding window helps this, where they say, well, technically, now any sequence here. So again, if we have this sequence and this is the next layer, actually, let's just draw. So this unit right here, it will be able to attend this and this, but not this and not this. But it will also be able to attend this and this, but not this and not this. Sorry, not this. So it'll skip one. So right, these attention patterns, they will always kind of skip one. And the idea is that now you have a vastly greater window of attention, right? Your window size is now way bigger. That means you can incorporate information way faster across the layers, like global information. But of course, now they're kind of arguing against each other. When they do this sliding window, they say, well, we pose that mostly local information is important for NLP, right? The words right around the word are important. And now if they say this here, they basically say, oh, well, it's not so important that we miss this word right here, which is right next to the word that they are attending from, which is counter to what they just said, that probably the most important information is around the word. They do get around this by saying, well, if we have different layers in a transformer, and in the lower layers we'll use this sliding window, fully local, and in the higher layers we'll use this dilated window. And therefore, in the lower layers, we postulate that local information is actually what's needed to understand local features. And then in the higher layers, we want more global information, because it will incorporate features from the local informations of the lower layers. All right, I can get the argumentation, but I feel that's just something they've thrown in there to make it work better after they tried it out. And the last idea here in the Longformer is what they call global attention. And this global attention is sparse. What it means is that there are some special units here. So in this, and this unit. And these special units, as you can see from the attention pattern, these can actually attend to everything. So this unit can attend, for example, to this one, or to this one, or to anything. These can attend to anything, and any unit can attend to those, right? Any unit can attend to the first unit right here. Right, so these are your special tokens, your special units, and they have global attention. And the reason for this particularly is that sometimes this is needed, and this is an engineering choice, right? The example I can give is, let's say you have a question answering task. In a question answering task, what you usually have is a question and a paragraph. And let's say the task here is to answer yes or no. Is the question, so the question might be a statement, right? I don't know. King James was king of England from 1120 to 1140. And then the paragraph will be the Wikipedia entry for King James. And the question is, yes or no, is the question true or not? Is the statement made true or not? How you would feed this to a BERT model, to a transformer, is you concatenate these two things, or statement and paragraph, right? These are the tokens right here. And then you would separate them using a special token called the separator token. This is just to inform the model that here is where the first thing stops and the next thing starts. And then at the beginning you would put a special token called the CLS token. Now, usually what you do is you send these things through your transformer, and now in the last layer, right, you end up, as we've seen before, because you always transform a sequence into a sequence, you end up with a sequence again. But you just want a single thing. You just want yes or no. So you designate, you say this particular unit here that corresponds to the CLS token. That's what I'm going to throw into a logistic regression, and that's what will give me my yes or no answer. And that's how you train it, right? So you don't want to single out any of these as like special. So you simply already include a special token at the beginning that then you take the classification from. right? It's pretty smart, but also you say, this is such a special token. I want that to be able to attend to anything, right? Even though, for example, this unit right here, it can only attend to its neighbors, right? It has this cone thing, and this unit right here has this cone thing. This unit right here can always attend to anything at each of the layers, right? It can attend to anything, and anything can attend to it. So it can get information from anywhere routed to it in each of the layers, and it can send information to any of the other units. Right? And this is an engineering choice. So at the beginning, you as an engineer have to say which one of these tokens are special tokens. And for these tokens, you'll actually then do full attention, right? It can attend to and from anything. So what are our new memory requirements? What this will give us is, first of all, we have n tokens, right? And here W is our window size. So we have n times W memory. But then we also add the global attention. So plus the number of special tokens times, right? So if there's a special token, it will have n times 2 memory requirement, because it can attend from and to in each layer. So, and this entire thing, sorry, with the plus, this entire thing times the number of layers. So this is your new attention memory requirements, and as you can see here, n plus n, so this is going to be order of n instead of much smaller than order of n squared as we had for the original transformer, right? So this is what the Longformer basically does. Now they have written custom CUDA kernels for doing this this dilated attention and so on, which is pretty cool, and they have code available for the model. They test this on a number of language tasks, and what I find interesting is they start from the RoBERTa checkpoint, which RoBERTa, where is it said? Somewhere, oh yeah, this RoBERTa model right here is a variant of BERT, right? You can see the name in here. Is a variant of BERT, and that's their baseline, and they start from these checkpoints as far as I understand, and they kind of copy over the position embeddings and so on, and therefore they only need to train not very much past the RoBERTa. Now the reason why they can copy it over actually is, and this I find very interesting, is they use a window size of 512. So until I read this, I got away from reading the paper thinking that this window size here might be fairly small, right? So this window size, it might be, you know, maybe 10, 20, 30 tokens or something, right? But actually this window size is 512 in their formulation, which basically means that this is as much as one of the classic models could take as a document, right? So, sorry, let's go over. So this here is 512. So this is what a classic model could take as an entire document. And in the classic model, you simply split up the document, feed chunks, right, and then aggregate over them. Now the Longformer basically has this. So right now, for now I said it has less memory requirements. Actually, it has the same memory requirements as a classic model, but it is also able, because of these global attention, to kind of incorporate information from the surrounding things. So that's the new part. Because if you think about it, if this W here is 512, 512 was the original N. So 512 was the N0, whatever the old models had as an N. So right now, if I replace this, and let's not take care of this. If I replace this, it's actually n times n0, and that regresses to the classic model if you plug in n0 here, right? So the new part really is the fact that you have this sliding window, and the global attention is able to incorporate information from these special tokens as well, because sliding window, that was done before. So I just don't want to get to you the wrong impression that now we can run transformers on like very small memory machines. We can't, but we can run them on the same memory machines because this is the same length, right? But also feed in longer documents and have some information of the entire document be propagated to these blocks, which before we couldn't. Before we could just simply feed these blocks as one and not have global information. So that's the new thing. At least they haven't tested it on the smaller things, which is cool from an engineering point, right? You would want to, because if you want to show that you're better, you would want to basically be able to be as powerful as the old model, but then be more powerful. And that's what they do. All right, so if you want to check out the experiments and the ablations, it's very interesting because they turn on and off a lot of things in their model and kind of check out where things come from, what helps, what doesn't. And I'll leave this to you and I'll link it. And with that, thanks for listening, watching, and bye-bye.